first, a few course announcements. Wow, that was right on cue. A few course announcements. Hopefully you're all on track for homework 5. The good news is that once you finish homework 5, there won't be any more homework except for the final project. So you should get that out of the way and then focus on doing an awesome final project. The other course announcement is that at the end of today's lecture, probably in the last 10 minutes or so, we're going to have the HKN folks come in and guide you guys through doing your course evals. It's very important for me, for the course instructor, and also for the TAs, for you to do your course evals. That's how we can improve the course next year, so do make sure to do that. And then on to the main event for today. So today it's my pleasure to introduce Professor Chelsea Finn from Stanford University. Chelsea actually did her PhD here at UC Berkeley. In fact, she actually co-taught this class back in 2016. But today she's going to talk about some more interesting, more speculative topics, hopefully to get you guys inspired for some ideas for your final project. Chelsea's research is focused on things like meta-learning, robotic learning, and reinforcement learning. She has done a number of pretty interesting things, like getting robots to learn end-to-end from pixels, getting robots to learn using video prediction models, and developing a bunch of interesting meta-learning algorithms. She's won a bunch of awards, which I'm not going to list out, and instead I'm going to, at this point, give the microphone over to her to get started on her lecture on rethinking reinforcement learning from the perspective of generalization.
Thanks for the introduction, Sergey. So today I'll be talking about rethinking reinforcement learning and thinking about generalization. And before I start, please feel free to ask questions throughout. I'd be happy to have more of a discussion. As Sergey said, this is more of a research talk and thinking about a lot of works that I actually are very new and I actually haven't presented before. So hopefully it will make it a bit more exciting. So I'd like to start off by telling a little bit of a story. And this is actually a story from here, from my PhD at Berkeley. So at the beginning of my PhD, I was interested in enabling robots to learn through trial and error. And in particular, our goal here was to enable a robot to learn a neural network that mapped from pixels from the robot's camera to torques applied at each of the robot's joints. And at the beginning, the robot doesn't really know anything. It's starting from scratch. It's waving its arm around randomly. And over the course of the learning process, it's able to figure out through trial and error how to insert this red block into the shape sorting cube. So we thought this result was pretty cool. The robot could figure out how to do the task, and you can see the final policy here, where the bottom right shows the image that the robot sees from its camera. And the reason why we were really excited about this result wasn't because it could figure out how to perform this task, but that it had an algorithm that could be used to perform many different tasks, and such that the robot could autonomously acquire tasks such as placing the claw of a toy hammer underneath a nail, such as screwing a cap onto a water bottle, and also a task in some follow-up work, such as using a spatula to lift up an object and place it into a bowl. And so, in principle, we had a general purpose algorithm that could enable the robot to autonomously acquire a breadth of complex vision-based manipulation skills. And a number of other works also built upon this kind of algorithm to perform tasks like hitting a hockey puck into a goal, opening a door, and throwing an object to hit a target. And in parallel, a number of other works were studying similar forms of reinforcement learning, but applying towards games and locomotion tasks. So this is really exciting. We can learn tasks autonomously through trial and error. Now, despite our excitement here, we have a bit of a problem. And the problem is that the robot didn't learn how to use spatulas to lift objects and to put them into bowls. The robot learned how to use that spatula to lift that object into that bowl. And if you gave the robot a different spatula or gave it a different bowl or even changed the tablecloth underneath on top of the table, the robot wouldn't be able to perform the task. It would have to start again from scratch to figure out how to solve the task. Now, so all these systems are kind of learning one task in one environment starting from scratch. Now you might say, okay, we can solve this problem. We just need to give the robot more spatulas, right? And then the robot will be able to generalize to different spatulas. But the tricky part is that behind the scenes, if you look at the learning process of many of these reinforcement learning systems, it looks a bit like this, where the robot tries the task, attempts it, and then the environment is kind of put back into some initial condition, and the robot tries again. And there are maybe sensors on some of the objects, and in many ways, it's actually a very manual process. For example, here, this is my friend Yevgen, and Yevgen is doing more work than the robot is doing here. And so as a result, it's not practical to collect a lot of data this way. It's not practical to collect data with many different spatulas, with many different objects in many different environments, such that our agents can generalize, and can generalize to the diversity of the real world. And so if we want reinforcement learning algorithms that can more broadly interact with the world, we need to kind of think about things a bit differently. So I would refer to these systems as specialists, and that they're very specialized towards one particular task in one particular environment. And I think that if we hope to have machines that more generally understand and can interact with a diverse real-world environment, then we may need to fundamentally rethink the kinds of algorithms that we're applying and the way that we're applying those algorithms to our systems. So what I'd like to talk about in this lecture is how can we rethink different aspects of reinforcement learning to enable broader generalization? Can we rethink the algorithms that we're using, the task representations that we're using, and the data that we're training on? And in particular, what I'd like to talk about is, can we recover something more general than a policy that allows us not just to do one task, but allows us to do other things? Can we learn task representations that have multiple purposes that can be used across different tasks, across different goals? And can we learn something from the success of ImageNet in order to learn generalizable representations? OK. So first, let's talk about rethinking algorithms. Can we learn something more general than a policy? So in the case of the spatula task, what the robot learned, the policy, the motion that it learned, couldn't be reused for anything else. It can be used for that spatula and for that object, but if you want the robot to do something else, it was very difficult to take that representation and take what was learned and actually transfer it to other things. So what do we want instead? I think that this is actually quite a difficult question. If we want something more general, something that can be reused and used for broader understanding, it seems like we want something that isn't just a policy. And so the perspective that I'll take on this, at least in this part of the talk, is it seems like we want something that we can use to quickly adapt to new concepts and new behaviors and new policies, such that if we have this representation, if we have this thing, then we can do a wide range of things and do things in a wide range of environments. So that seems pretty reasonable. So maybe one thing we could think about is having a policy that's conditioned on a task. Then we could probably adapt it to lots of different tasks. Although one of the downsides is that if we want, you can only adapt it to the kinds of tasks that you trained it on. And so it seems like we might want something else. It seems like we might want something like a prior over policies, because if we have a prior over policies, then we can maybe learn something new. And leverage that prior experience, leverage your prior information to quickly adapt to a new situation. And so that's what we'll talk about. And in particular, the perspective that we can take on learning priors over policies is the meta-reinforcement learning problem. And I know that this was covered in the course, so I'm only going to kind of recap this problem statement and different algorithms very briefly, and then talk about some of the challenges of meta-reinforcement learning and how we can try to address some of those challenges. So what is the meta-reinforcement learning problem? So first, let's start with the reinforcement learning problem. In many ways, you can view it as trying to learn a policy that maps from states to actions, using some experience that you collected that has states, actions, and rewards. Now, you can view the meta-reinforcement learning problem statement as follows. So in meta-reinforcement learning, our goal is to quickly adapt, to learn a prior from our previous experience that allows us to quickly learn new tasks and quickly adapt to new environments. And so the way that you can view this problem is one that takes in some data, some experience from in a new environment, in a new task, and uses that data to quickly learn a policy for a new task, where you use that data and then you want to be able to map from states to actions. So you can view the meta-reinforcement learning problem as being able to acquire something that takes an experience and produces a policy. And then the way that you go about doing this is through a data set of experiences across different tasks, where each of these individual data sets has kind of rollouts that you collected from these tasks. And then the kind of challenge with these meta-reinforcement learning algorithms is both to design and optimize this algorithm F that takes an experience and produces a policy, as well as collecting the appropriate data for a new task. Essentially learning how to explore for a new task. Okay, so this should mostly be a review. And one of the things that I believe was also covered in this course is the model-agnostic meta-learning algorithm. And you can see kind of an illustration of it where at the end of meta-training, you learn a policy or a prior that allows you to quickly adapt to new tasks, such that if you take one gradient step with respect to the task of running backward, you can get a policy that looks like this. And if you take one step with respect to the task of running forward, you get a policy that looks like this. So you can very quickly adapt to different tasks. Now, one of the big challenges with many of our existing meta-reinforcement learning algorithms is data efficiency. So this adaptation process is extremely fast, but the process of acquiring a prior over policies can require a very large amount of data itself. And so even though it can, at test time, you can learn with just a few gradient steps, each with a small amount of data, so very excellent meta-test time efficiency, and many times the meta-training process requires hundreds of millions of steps. About a month of time if this was in real time. And this trend isn't just true for the model-agnostic meta-learning algorithm, but is also true for other algorithms like RL squared and ProMP. So you can see kind of the x-axis here has like 10 to the 7 or 10 to the 8th time steps. And one of the algorithms that you learned about a couple weeks ago was the Perl algorithm, which is significantly more sample efficient, so around 20 to 100 times more sample efficient. And the way that this algorithm worked was it contextualized experience into a latent context for a new task, and then trained this latent variable policy using efficient off-policy algorithms such as soft actor critic. OK, so that was a brief overview of kind of the current status of meta-reinforcement learning, which should mostly be a review. And now let's think about, well, have algorithms like MAML and Perl allowed us to accomplish our goal of making policy adaptation fast, allowing us to learn something more general than a policy that allows us to quickly adapt and generalize to new contexts and to new tasks and to new environments. And I think that in some ways they have, but in many ways, I don't think we should be satisfied with these algorithms. And in particular, these algorithms allow us to adapt to new variations on tasks, but we haven't seen them allow us to adapt to entirely new tasks. So if we want to be able to kind of completely learn a new task, we need to maybe actually deploy these algorithms in different settings. And so in particular, if we want to be able to adapt to new tasks, we also want to be able to generalize. So we need our meta-training task distribution to match our meta-test task distribution in order to be able to generalize to the test tasks. And so if we want to be able to adapt to entirely new tasks and also to be able to effectively generalize, we need both this distribution match as well as a very broad distribution if we want to be able to generalize. So with this in mind, I think one thing we need to think about, or kind of the first step, is can we actually start meta-training across distinct task families? So rather than meta-training within like locomotion behaviors of running in different directions, can we meta-train across completely like qualitatively distinct tasks in a way that might allow us to start generalizing to new tasks? OK, so for example, one thing we might try to do is maybe we have some simulated manipulation environment where we have this yellow robot gripper here. And we want to be able to meta-learn priors across the space of manipulation tasks. So for example, we may want to be able to grasp objects, press buttons, slide objects across the table, or stack two objects. This is kind of a space of tasks that we could consider doing in this environment. And then our goal will be to learn a new variation of one of these task families using a small number of trials and sparse rewards. So we don't want to have to require very detailed reward information, because that can be very costly. And so we want to be able to meta-train across these task families and adapt to a variation of one of them using a small amount of experience. All right, so this seems pretty reasonable. This follows kind of the standard meta-reinforcement learning problem statement. But we have a bit of a problem, which is that if we're considering sparse rewards, the robot will need to explore every possible task in order to figure out what the goal is, right? If we didn't tell it what the task is, if we didn't tell it which of these 4 things it has to do, it has to actually try all of these 4 things before it will receive any reward. And this is a bit silly. And if you were to kind of scale this up to kind of a real world situation, maybe something that looks like this, the robot would have to poke every single object and try every possible task before it can figure out what the task is. We're kind of making it artificially hard on the robot. We're not even telling the robot anything about what it has to do. So maybe one of the things that we could do is reformulate this problem. We could reformulate it as learning from not just trials, but also learning from some specification of the task. And the way that we can specify the task is by showing the robot what task we want it to do. So in particular, can we not just learn from trials, but learn from one demonstration that can specify the task, and a few trials that can allow the robot to practice that task in a way that allows it to learn an effective policy. OK. So the demonstration will be used to convey the task, and the few trials will be used to figure out how to solve it. OK, so we want to learn from one demonstration and a few trials. So what this will look like at test time is the robot will watch one demonstration. It will then try the task in a new situation, such as a trial like this. So it knows that it needs to do something like the left. It might try to accomplish the task by sliding the teacup towards the other cup. Then it may get a reward of -1 or a reward of 0, saying that wasn't quite the task. And then it can figure out, using that trial, which wasn't successful, that it should actually be pushing the cup towards the teacup. OK, so if this is the kind of behavior that we want, how can we prepare for this? So if we want to be able to learn from a demonstration and a few trials, we need to be able to train for the ability to adapt with a demonstration and a few trials, right? We want training and test time to match. We also want to be able to do this in a way that is scalable. We don't want to have to collect many, many trials of experience in order to solve the task. So the way that we'll formulate the algorithm is we'll collect demonstrations, a small number of demonstrations for many different tasks, where different tasks will correspond to sliding different objects, pushing buttons in different positions, grasping objects, and stacking objects. And then we can train a one-shot imitation learning policy, so a policy that's conditioned on a demonstration to be able to solve that task from that one demonstration. Now, it may not be able to completely perform this task if the demonstration is ambiguous, like in the setting on the top, but it will be able to narrow down the realm of possibilities of what the correct task may be. And then, using this one-shot imitation policy, we need to also be able to learn not just from demonstrations, but also from trials. So we'll collect trials for each of these tasks by running our one-shot imitation learning policy to see kind of the kinds of behaviors, the kinds of trials that might correspond to this task. And this will be a batch off policy setting where we just collect a batch of trial data for all of the tasks. And then lastly, we can train this retrial policy, or a policy that can adapt both with a demonstration and with a trial, using a imitation learning objective in the outer loop. OK, so essentially, if you kind of take the meta-training setup before, your detrain will correspond to, in this stage, will correspond to one demo and a few trials. And the outer loop will be trained with imitation learning. OK, any questions on how this is set up? Yeah?
You mentioned the case of -1 + 1 rewards. So maybe this isn't something that's been looked into too much yet, but in multitask learning and multitask transfer learning, there's a big issue with reward schemes being different with the training tasks, and how you can really bias your policy toward doing really well on something with really dense or really high magnitude rewards. Do you foresee that being an issue with this as well?
Yeah, so that's a really good question about basically how can we think about is different reward scales a problem in this sort of setup? So in this particular setup, we're using a sparse reward that's basically, we're actually not giving it -1 rewards, we're either just 1 or 0. 1 if you solve the task and 0 otherwise, and so the magnitude is the same across all the tasks. But perhaps more importantly, we're not actually running reinforcement learning here. We're training it to be able to adapt very quickly with the trial, but all of the kind of supervision is coming from an imitation learning objective. So in that case, we don't have to, in this problem setting, we don't have to deal too much with this sort of imbalance in reward scale, but that's definitely a problem that comes up, and I'll touch on that a little bit in one of the future things I'll talk about. Okay, so how does this actually do? So what we wanted to look at is this algorithm, which we're calling watch, try, learn, in the sense that you watch a demonstration, try the task, and then learn. To first meta-reinforcement learning that tries to only use the trials to accomplish the task. In this case, you have a hard exploration problem because you need to try all of the tasks. And we also want to compare it to meta-imitation learning. Do the trials actually allow you to improve on the task in comparison to just seeing a demonstration? And then lastly, we can compare it to a very simple approach of just trying to match all of the demonstrations and don't use any meta-learning, just behavior clone all of the demonstrations that were provided. And quantitatively, what we can see is that first, the algorithm is able to learn across all of the distinct task families effectively, in comparison to previous methods that are just learning within one task family different variations of that task. And second, it is able to significantly outperform using only trials or only demonstrations. So only demonstrations is shown in orange, so you can see the difference between the blue and the orange bars. You can see a significant gap there. And then only trials actually perform so poorly that we didn't plot it on this example, or on this plot. And then qualitatively, you can see some of the behaviors. So this is the sliding example that I showed previously, where the demonstration, which is provided with teleoperation, is shown here. The robot can then try the task, such as this, for example, trying to push from the left towards the right. And then it can learn from that to figure out that the correct thing was to actually push the teacup towards the cup. And here's another example. So here the robot is given a demonstration. The goal here is to grasp the object, which you can infer from this demonstration. That it attempts to grasp the object but isn't able to grasp it from just seeing the demonstration. But using the demonstration and the trial, it's able to adapt its policy in a way that allows it to successfully perform the task. Okay. And then the last comparison we wanted to run is initializing with behavior cloning and then fine-tuning with reinforcement learning. This is kind of a very typical approach that you might take if you want to learn from both demonstrations and trials. Just train with imitation learning on the demonstrations and then fine-tune with reinforcement learning. And if you do this, it requires around 900 trials in order to accomplish the task, in comparison to using one trial, which WTL uses. So this significantly accelerates the reinforcement learning process. Okay, now that I talked about how we can learn from demonstrations and trials, I'd like to take a little bit of a tangent, which is in some ways a little bit of a dirty secret of meta-learning that a lot of practitioners know about, but people often don't talk about. So in the WTL setup, the demonstration was partially specifying the task. So it was giving an indication of what the task family was, but wasn't necessarily telling you exactly the way to solve that task family. For example, which object to push towards the other object. It was inherently, there's a little bit of ambiguity. And as a result, because there was some ambiguity, the meta-training process was required to use the trials in order to accomplish the task. The trials needed to be used to reduce its uncertainty about what the actual task was. Now, what would happen if the demonstration fully specified the task? Does anyone have any ideas on kind of what behavior the algorithm would learn if you can fully determine the task from the demonstration? Any thoughts? Yeah?
Would pick only that color of the cup in this example? take this complete specifications to pick the green cup, and then in retrials it will only pick the green cup and you want to go to the other colors? Like the ambiguity that there was initially, there's no ambiguity now, so there's no exploration being wanted to do basically.
Yeah, right. So if it's basically fully specified from the demonstration, then it will only the trial policy will only grasp the green cup, because that's kind of very clearly the thing to do in the demonstration, that based on the demonstration, and then it won't actually need the trials to accomplish the task, right? And so essentially this reduces to just one-shot imitation learning, where you're given a demonstration, you want to learn a policy from that demonstration. And in particular, the algorithm can just ignore the trials during meta-learning. So even if it's given the trials, in order to learn from, it can just ignore those and just use the demonstration in order to accurately get good training performance. Now, this may be completely fine, because, for example, if you're good at the meta test task, like you're given a demonstration for a new task, and then you can perform that task quite well, then you're fine, you're done. You have a policy that can perform the task, right? But things get a little bit more tricky when you're not perfect at the meta test. So maybe you see a demonstration like that, and then the robot doesn't quite solve the task. It can almost solve it, but can't quite solve it. If you're in this setting, then you're a little bit stuck, because you learn to do one-shot imitation learning, and you also learn to ignore any trial data. And so if you try to then adapt using this trial data, your algorithm doesn't know how to use it. It just ignored it during the meta training process, right? And so this is a bit of a problem, because your robot failed and it doesn't have any means to adapt quickly. Now it needs to run fine-tuning with reinforcement learning, for example, which could require hundreds of trials. And the problem is actually a little bit more general than this. So if you imagine meta-learning as, in general, thinking about adapting with data and taking an input learning from an input and from data to make a prediction, then if you don't need your training data to solve the task, if all that information is in X, then you can just ignore the training data and just learn a function that directly just takes an X and solves the task using that. And so maybe to make this a little bit more clear, let's look at another example. So say we want to be able to predict the pose of objects. So we kind of meta-train it across a lot of different types of objects in order to predict the pose. So we want to be able to, given a small amount of data corresponding to image and label for the pose of that object, we want to be able to predict the pose for new images, right? And one of the things that's tricky in this sort of thing is you can actually just ignore the task training data, memorize the canonical orientation of that object, and output the pose of each of those objects. And this would work out just fine on the training data set. You would be able to output the pose of all the objects in your training data set. But then when you're given a new object, you don't know the canonical pose of this object, then you wouldn't be able to make predictions about the objects. You don't know the canonical pose, and you won't know how to adapt from data because you didn't learn how to adapt from data. The meta-training process just ignored the task training data on the left and just tried to make predictions about the images on the right. OK, so does this problem make sense? Essentially memorizing information about the training tasks in a way that allows you to just try to classify them in a way that ignores the task training data. Now, is there anything that we can do about this? So one thing that we can do is we can take an information theoretic point of view. If we view the meta-training process as learning this function, then we can recognize the problem occurs when your prediction isn't using the training data. Essentially, when the mutual information between your predicted y and the training data conditioned on your input and your parameters is 0. And with this definition, you can then regularize this quantity to be not 0 and actually resolve this problem. So on the pose prediction problem on the left, if you train meta-learning algorithms on this, like conditional neural processes and MAML, you get actually quite poor performance in terms of the mean squared error of your prediction error. But if you're able to regularize them, regularize this information quantity, then you can actually solve the task effectively and be able to effectively predict the pose of the object. And this isn't just as simple as standard regularization. So you could also take standard regularization like weight decay and Bayes by backprop, apply that to the meta learning algorithms, and it won't solve the task. Yeah.
Is that the error in degrees?
This is the mean squared error. I can't remember. I think it's in degrees. It may be. It's possible that it's in radians, but I think it's in, I don't think radians would make sense. I think it's in degrees. Yeah.
Do you calculate the mutual information exactly, or is that an approximation somehow?
Yeah, so you can't, good question. This isn't something, or we haven't found a way to calculate it exactly, and so we've formed an approximation to it. And I'd be happy to talk about the way that we actually approximate that offline if you want. Okay, cool. So we talked about, that was a bit of a tangent. We talked about how we can train across broad task families. And WTL allowed us to train across these 4 distinct task families. But what if we want to actually adapt to entirely new tasks? So we were able to generalize within those 4 task families. But now, if we want to adapt to entirely new tasks, we don't just need a broad distribution of tasks, but we also need a distribution of tasks that is more densely covered than the 4 distinct task families that we had before. So how can we think about getting task distributions that are broad and also somewhat dense? Well, there are a few options, potentially. So there are various open source frameworks that provide different tasks. So there's things like OpenAI Gym and like the Atari suite, for example. But both of these options aren't very satisfying for meta-learning purposes because the tasks don't share that much in common. So learning to walk with an ant versus learning to walk with a half cheetah, they have completely different degrees of freedom. And as a result, it's maybe hard to recover the structure between them. And likewise, different Atari games have completely different environments, different visuals, different representations of objects. And so trying to actually learn priors across these environments, while there are a lot of Atari tasks, would be very challenging. Something that I think is also a step in the right direction for thinking about meta-learning in particular is this benchmark right here, which is the RoboSuite set of tasks that has a set of manipulation tasks. But the challenge is that it contains, I think, only around 6 tasks, which isn't as densely covered as what we need for meta-learning. So if we want to think about meta-learning across broad and dense task distributions, I think we want a few different things. So we want many different qualitatively distinct tasks. So I'll put out 50 there, but that number is somewhat arbitrary. We want reward functions and success metrics. They don't necessarily need to be shaped reward functions, but we want some metrics that we can use in combination with reinforcement learning. We want the tasks to be individually solvable such that we can focus on transferability and focus on learning priors in a way that allows us to quickly learn new tasks. And we also want some shared structure, such as a unified state space, unified action space, in order to better facilitate transfer and make it easier to learn the structure among these tasks. And so with each of these desiderata in place, we developed a benchmark with 50 manipulation tasks that kind of accomplishes each of these points of motivation that may allow us to actually start studying the ability for meta-learning to adapt to completely new tasks. Yeah?
So it seems like you had different robots, like the numbers of joints or something, you might have like a different action space or state space. Like, do you think that like meta-learning should be able to apply to those kind of cases too?
Yeah, absolutely. So I think that it would be awesome to have to allow learning priors across robots, and I think that we should be able to do that. And I think that in many ways, there may be a lot to be shared across different robots, especially if you're doing the same task. And it would allow us to collect a lot more data. And so I'll actually talk a little bit about multi-robot learning towards the end of this lecture. But for the purpose of this, I think the meta-learning algorithms aren't quite there yet. We can't do this yet. So kind of existing algorithms show some signs of life, but there's still significant room for improvement. But I think that if we can start to solve these tasks, then we can move towards learning across robots. Yeah.
So what about like sequential and hierarchical tasks? So like, for example, if you say fetch a ball and then you want to throw it away or something, or you fetch a ball and then you want to keep it, like this kind of hierarchical or like sequential task, is there any way to deal with it? Because I believe like a lot of like real world tasks, they're like compounded with like you know, like the first task, second task, and third task, and then you can just make a lot of combination with that, and then it just will make the meta world like a lot more realistic.
Absolutely, yeah, absolutely. So I think that if we, well, one, it would make it more realistic, and two, it also make it very easy to create a combinatorial number of tasks. So here are 50 tasks that are all kind of primitive tasks, and if you start sequencing these together, then you can get a much larger and broader space of tasks and also a denser space of tasks. So I think that's a really important direction for future work. Yeah. Yeah, that's a really good question. I don't know how to measure kind of how densely you're covering a task space. And I think that one of the challenges there is that a metric on tasks is going to be intimately tied to the optimization process. And so you need to be thinking about, after learning a set of tasks, how easy is it to learn a new task? And measuring that in a way that is meaningful and tied to the optimization process, I think is very challenging. I think that qualitatively, this is more dense than having 4 distinct tasks of similar flavor, but in many ways, it's hard to actually quantify that. And it may be that this is, whenever you develop a benchmark, it's hard to know if it will actually be useful, because you need to see, for it to be useful, there needs to be the ability to see progress in the future, and it may be that it's too hard or too easy. But I think that this may be at least putting something out there such that we can start to iterate on understanding what it means to be a dense distribution versus a sparser distribution. OK. Great. So hopefully this will allow us to actually meaningfully study broad generalization in meta-learning algorithms. So to kind of recap this part of the lecture, I think that scaling to broad task distributions is tremendously important if we want to meaningfully study this problem, but also very difficult, and it can't be taken for granted. And in particular, some of the things that I think that we need to be thinking about is conveying task information beyond the reward function and allowing algorithms to intermix this task information that's provided by a human with trial and error experience. To do that, we may need to regularize the information flow to allow it to incorporate trial and error experience, even when the task information tells us a lot about the task. And we also need to be thinking about training on very broad and denser task distributions, such as MetaWorld and hopefully other benchmarks in the future. OK, so now that we've talked about algorithms, what about task representations? So in meta-learning, you're essentially learning the task representation. But is there a way to convey task representations in a more direct way from a human? So a number of works have looked at different ways to specify tasks. So this could be, for example, using a one-hot task ID, as is done if you study the multitask version of MetaWorld. You could also convey it with a reward function, with an image of the goal, which is what we did actually in the spatula task, or with demonstrations. These are all kind of pretty typical way to specify tasks for behavior. But they all, I think, have some downsides. So a one-hot task ID allows you to kind of very clearly enumerate the tasks and is very simple, but it precludes generalization to new tasks. If you give it a new task ID, it doesn't know, the agent won't know what you're talking about, right? Reward functions also can preclude generalization. They preclude zero-shot generalization. The robot would actually need to try the task in order to solve it. And they're also somewhat hard to provide, and they're not intuitive for kind of average humans in order to think about formulating. Images of goal allow you to generalize, and in some ways they can be easier to provide, but they require you to solve the task, which is maybe a bit silly. You actually have to solve the task, show the robot what the final goal is, and then have the robot solve it. So that doesn't really seem like the representation that we want. And demonstrations, likewise, also involve solving the task and can also be hard to provide. So how can we think about tasks that allow us to generalize and that aren't that hard to provide? So what about something like language instructions? So language is easy for humans to provide. We can just tell the robot what we want it to do. It's also very easy to specify many different tasks, a very large space of tasks with language. We just have to write down a list of the kinds of things we want robots to be able to do. And lastly, it also allows us to generalize. So if you can recognize the compositional structure of language and generalize to new sentences, well, if you can recognize the compositional structure of language, then you can generalize to new sentences. You'll understand what a new sentence means after experience with other sentences. But the challenge is then, if we want to do language, we have to deal with language. We have to deal with the complexity of language, right? So how hard is it to deal with language? And that's what I want to talk about in this part of the lecture. So first, we need an environment if we want to learn language-based skills. And there isn't really any kind of existing benchmark, at least in the space of object manipulation, for example, that allows us to study this. But we could take some inspiration from other work. So there's this popular benchmark in the space of vision and language for reasoning. So this benchmark looks kind of like the image on the left, where you want to be able to answer questions about the positions of objects, the number of objects, and the size of objects. So what if we take some inspiration from this? So that's what we did. We developed the Clever Robot environment, and we basically plugged this sort of environment into the Mojoko physics engine, such that we can think about answering these questions or changing the environment such that these questions are true using interaction with the environment. OK, so how do we go about doing this? Can we learn policies that are conditioned on a language sentence, on an instruction? So one kind of naive thing that we could do is just kind of train with reinforcement learning, give it an instruction, train a policy for a wide range of instructions. But one of the challenges there is that if we're doing this with reinforcement learning, if we're giving it an instruction and telling it to do that, if we have a very large space of instructions, then the chance of us actually performing the instruction that was given is very low. So we have a very hard exploration problem because we need to actually figure out, we need to kind of actually solve the instruction that was given to us. And so one of the things that we can think about is how can we provide a little bit more supervision in a way that allows us to make the exploration problem easier in order to solve this problem with reinforcement learning. And so what we're going to do is during training time only, we're going to assume the ability to sample questions in the form of language and get answers to those questions about basically whether or not the state of the environment is kind of respects that question. And then we'll get a sparse reward of whether or not an instruction has been achieved. So in particular, say this is our current state. The white ball is our agent that can push around the other objects in the environment. Then we're given some instruction, which is in the form of a question. So here's a red ball. Are there any matte scion spheres to the right of it? So right now, this is false, because the scion sphere is in front of the red ball. Then the agent performs an action, such as pushing the cyan ball to the left. This doesn't accomplish the instruction, so we wouldn't get any reward. And so if we were training with standard reinforcement learning, we wouldn't be able to learn anything using our policy. But as a result of this, we did actually change the answer to other questions. And so for example, this doesn't satisfy the input instruction, but in hindsight, it accomplishes other instructions. So for example, you can imagine the question, there's a green sphere. Are there any rubber cyan balls in front of it? This is something that it did accomplish. And so in hindsight, you can recognize the fact that you accomplished that instruction and not the other instruction. And so you can relabel this transition with the instruction that it achieved and include both this instruction as well as the one that it didn't accomplish in the replay buffer and use this for training your reinforcement learning agent. So here you would get a positive reward. For that one, you would get a negative reward. And so you get data that both accomplishes some instructions and doesn't accomplish other instructions. And that, in particular, the ones that you accomplished in hindsight will drive the learning process and make exploration much easier. Yeah?
So what is achieving an instruction? It's like the agent decides yes to that answer, to that question?
Yeah, so in this case, achieving the instruction corresponds to changing the world such that the answer to that question is yes. So you could also imagine these as sentences instead of questions. We decided to use questions for this work to more closely follow the Clever engine, but you could very simply reformulate these questions to also be sentences or commands. Yeah?
Is the question and answer only from Clever, like those restricted set of questions that you have?
Yeah, so that's a great question. So in this case, we were using language that was programmatically generated from a space of language, using and actually leveraging the Clever engine. And there was still significant variety, for example, mentioning like attributes of objects like rubber and mat, but it still is a restricted set of instructions. We were considering on the order of thousands of instructions in the entire space. Yeah.
Did you try embedded languages, so embedded representations instead of plain text language? So like log embeddings of word embeddings.
Yeah, so in this case, we actually pass in embeddings of each word rather than the word itself. And that we found that worked well. OK. So in our experiments, there's a couple questions that we want to answer. The most important question is, how can we evaluate if compositionality of language is important? And does this actually give us anything over the other possible representations that we could use for the goal? And so to study this question, we compared to a few different things. One is just a one-hot representation of the goal. This is kind of the first kind of version of you can imagine of a goal. And the second is a non-compositional representation of the goal. So in particular, the way that we wanted to study, can you get a non-compositional representation of the language and condition on that representation instead? So what we did is we took a sequence-to-sequence autoencoder. We passed in the language as input, and then trained it to reconstruct that language. And then we used the learned representation, the bottleneck right here, as the thing that we would condition our policy on. And so this is something that encapsulates all of the information of the language. It's a compressed representation of the language, but it may not exhibit the compositionality that the language tokens have, that the sentence has, right? So this would allow us to kind of ablate this. By studying this, we're still giving it the same exact amount of supervision as our method, but it's a representation that doesn't have the compositionality of the sentence. OK. So if you look at the learning process or the learning performance of this instruction conditioned learning, what we can see is that this is the learning curve. The x-axis is the number of samples. And the y-axis is the number of instructions it can achieve per episode. And what we see is that by using kind of the language and using the hindsight relabeling that I mentioned before, we're able to learn very effectively. And in comparison, if you use one-hot goals, or if you use with relabeling, or using the non-compositional representation also with relabeling, we perform much worse. And so compared to language-based goals, the one-hot representation struggles to learn, and the non-compositional representation also struggles to learn, despite having the same exact supervision as using the language sentences. So learning is easier with this because of the structure. And we actually can also generalize. So with one-hot representations, you can't generalize to new instructions by definition. But if we also compare to the compositional language instructions, so we compared both kind of a standard train and standard test where we hold out instructions from the same distribution. And then we also looked at out-of-distribution generalization. So this column is showing a training set where the word red is never in the first half of the instruction. And this is showing instructions where red is always in the first half of the instruction. And what we see is that basically the language leads to more compositional representations and allows for better systematic generalization. So both of them generalize pretty well to the test instructions. But when you test on basically on extrapolation performance, we see a drop in both of the methods, but we see a much smaller drop for using the language representations in comparison to using the non-compositional representation. OK. Cool. So to wrap up that part, I think that language-based task representations, while it seems like language may actually make things harder for the algorithm, what we find in practice is that it may actually make things easier for the algorithm as well as easier for the human or the user. OK. Now, lastly, I want to talk about data. So what does the data that we pass into our reinforcement learning agents look like? So if we look at kind of the examples that I showed at the beginning of my talk from 3 to 4 years ago, the data looks something like this, where we have a single object. So the kind of entire world of the agent is that single object. We have a single environment. and a single task. And as a result, you can only expect really generalization to that single task for that single object in that single environment. Now, more recently, we've seen works that trade across many different objects. So we have many objects, still a single environment, and still a single task. So we're making some progress. We're able to now kind of generalize across objects. And then even more recently, we've also seen methods that have many objects, single environment, and many tasks. So we're actually trying to start to generalize across objects and across tasks. But in each of these examples, we still have a single environment. So we're making a lot of progress in terms of the data that we're training our agents on in a way that facilitates generalization. But if you look at these data sets and compare to kind of take a machine learning point of view, you can compare them to something like ImageNet, they really aren't comparable, right? And so if we're training our reinforcement learning agents on the data on the left, we can't expect the generalization that we get when we train models on the data on the right. And so we have significantly limited the diversity of the data set to a single viewpoint, to a single environment, in a way that prevents us from generalizing broadly. So clearly, we need more diverse data if we want to generalize more broadly. But the caveat is that if you take the robotics point of view, you don't want to have to collect ImageNet for your robot, right? And so we have this current paradigm of setting up an experiment, collecting data for that experiment, and then running learning, and then kind of rinsing and repeating, right? And can we think about starting to accumulate and reuse broad data across labs, right? So if we want to collect ImageNet, it isn't going to be practical to collect ImageNet in each of our own individual labs, on each of our own individual robots. In general, with reinforcement learning, it isn't practical to collect ImageNet for your one reinforcement learning experiment, right? So if we care about generalization, we need to start thinking about accumulating data and reusing data across experiments rather than in the context of a single experiment. Now, in the context of robotics, one of the challenges here is that each lab has their own robot, right? And so that means that if we want to be able to share data across labs, we also need to be able to share data across robots. So is that even possible? So to study this question, we wanted to figure out, can we accumulate and share data? And to do this, we need to first collect a data set. So we collected a data set that looks a little bit like this. And the data set has 7 robot platforms. It was collected across 113 camera viewpoints with 15 million video frames. And it was also collected across 4 different institutions: UC Berkeley, Stanford, Google, and University of Pennsylvania. And so we're hoping that this will start to allow us to study generalization in more meaningful ways and allow us to start to study, can we actually accumulate and reuse data across labs? And importantly, this data set is open for contributions, so we're not just limiting ourselves to one kind of fixed data set. Now that we have a data set, that we need to kind of actually answer this question. Can we actually use this data to do something useful? So to do this, we looked at, we need algorithms that can learn from batch data sets and not require you to collect data for each iteration of your algorithm. And so what we did is we used a visual model-based reinforcement learning algorithm that uses a data set. It learns to predict using that data. So it learns a video prediction model that can generate predictions that look like this. This is something that you can do with a single batch data set. You don't need to collect on-policy data to do this. And then once you have this predictive model, you can plan using this model to accomplish tasks. So if you want to, for example, push this black object over to the right, you can sample a bunch of potential action sequences and find the one that will allow you to accomplish that goal. OK. So this is essentially visual model predictive control, which I think was briefly covered earlier in this lecture. So it's just model-based planning in the space of images. OK, so this is the method that we'll use to try to see if we can actually use this broad multi-robot data set. So we're going to take the data set. We're going to hold out one of the robots, and then fine-tune on one of the other robots. So we want to be able to test if we can generalize to a new robot. So we hold out a robot, fine-tune our video prediction model on a new robot. And this isn't just fine-tuning to a robot. It's also fine-tuning to a new environment, to new objects, to a new viewpoint, essentially fine-tuning to an entirely new experimental setup. And then we want to evaluate the model that was fine-tuned on that experimental setup on a range of tasks. And so we can see some of the results here. So the bottom row is showing if we do this pre-training and then fine-tuning, we get around 40% success rate on the set of downstream tasks. And in comparison, if we train from scratch on that robot, on that experimental setup on the bottom, we do significantly worse. And we do actually worse if we have the same amount of data, and we also do worse if we have more data, if we have 4 times more data on that robot. And so here we're seeing the benefits of actually pre-training on a much more diverse data set. And likewise, if we do an experiment on the Franca, so we hold out the Franca, we get, again, around 40% success. And in comparison, randomly initializing the network and training only on Franca data does worse. And we see the same trend on a Baxter robot as well. So kind of the takeaway here is that in contrast to learning in a single environment with a single object, we're able to kind of take a step towards more generalizable skills in more open environments. OK, so this is pretty cool. We can start thinking about scaling up towards large data sets. Can we use other data? So if we think about what other sources of data are available that we could actually use for robots, what about videos of humans? So maybe we have a video like this, or a video like this. We have tons of these videos on the internet, for example. And it seems like this data should be very useful for robots to learn from. It's certainly very useful for humans to learn from. Humans watch these videos all the time in order to learn tasks. And so the benefits of this kind of data is that it's a very broad and untapped source of data. And it also includes very sophisticated interactions, such as cooking and using tools. And so it seems like we should be able to learn both how to generalize and also learn how to perform more complex tasks from this data. The challenges, though, which you probably recognize, is that there's domain shift between what the robot looks like and what the human looks like, between the robot's environment and the human's environment. And we also can't really directly access the actions that were taken by the human, in contrast to interaction data that we might have on a robot. So to try to start to study this problem, we wanted to take a first step, which was to consider videos of humans, sorry for the low resolution here, but videos of humans doing tasks in the robot's environment. So here there's still going to be domain shift between the robot and the human's appearance, but the environment will look the same. And we also won't be able to directly access the actions that the human took. And in particular here, the robot will be learning how to use, will be showing how you could use tools to accomplish tasks. And we'll also want the robot to figure out how to use tools and how to perform tasks using this data. OK, so in particular, the way that we'll formulate the problem is learning from both the observation data of the human and interaction of the robot interacting with the world. We'll then train a video prediction model using that data and plan to accomplish tasks. Now, how do we combine these two sources of data into our model? We can formulate a graphical model. If we want to learn an action condition video prediction model, we can observe the states or the images. We can sometimes observe the actions. So we'll have a semi-observed variable for the actions. And then we'll also have a domain variable that will indicate whether or not that video came from a human or whether or not it came from a robot. OK, so if we can formulate this graphical model, we can then essentially augment our video prediction models with these latent variables for the actions and for the domain, and then optimize the evidence lower bound of that graphical model. OK, so this provides us a kind of a principled way to fuse these sources of information. Now, does the model actually leverage the observation data in order to improve? So this is kind of the key question. Can it actually use the observation data in addition to its own interaction in order to perform better? And what we see is if we look at kind of standard video prediction metrics, such as PSNR and SSIM, where higher is better in each of these cases, by using both the random data and the human data, using this model, we're able to achieve performance that is significantly higher than only using the random data, which is shown in the second row, and in comparison to other approaches that use both random data and human data. We can also start to approach an oracle that uses kind of kinesthetic demonstrations of using tools as well. Okay, well, these metrics aren't that useful, but they still allow us to kind of quantitatively evaluate this sort of thing. Perhaps the more important question is, does the observation data allow us to improve task performance? And so then we use this video prediction model to try to perform tool use tasks. So we give a task like this, where the goal is to push some objects over to the right such that they're all clumped together. And then the robot can figure out, using this video prediction model, how to accomplish the task by using the pencil case as a tool. And likewise, we can try to perform a task like this, such as pushing a pear onto a plate using a spatula, so we can see a result like this. And likewise, here's a third task where the goal is to use a tool to push trash towards a dustpan. Okay, and then quantitatively, we can see that by leveraging the observation data, we get around 40% success in comparison to a model that only uses the interaction data and gets 23% success. Okay, so kind of the takeaway here is that we should be able to allow our reinforcement learning algorithms to accumulate and use all of the available data. This includes data from robots at other labs and data from humans. And this idea isn't really that revolutionary. I think that really this is just taking robotics kind of out of the dark ages of machine learning. Kind of the rest of the machine learning field is already accumulating and using broad data sets and using use those to train our models. And really the goal of this is to move robotics to that phase of machine learning where we can use broad and generalizable data sets. Okay. So to wrap up, I talked about rethinking algorithms, task representations, and data in order to increase the generalization of our reinforcement learning agents by scaling to broad task distributions, by using language-based goal representations, and by accumulating large and offline data sets. And I think that by doing so, we can take a step towards agents that can more generally understand and interact with the environment. And since I also had some slides on open challenges, but I think that since we're out of time and you should take your course surveys, I will thank my students. I have a few minutes? Oh, right. You guys end on time. Sorry, I'm used to Stanford, where Stanford ends 10 minutes early.
We start 10 minutes late.
Yeah, so Stanford is on time. So, OK. So let's talk about open challenges a little bit. OK, so how do we think about open challenges for robots, beyond all the challenges that I mentioned in the talk? So one way I like to think about this is a very concrete example. So say we want a robot to go into an environment. Here's our robot. Maybe the environment is a new kitchen that the robot has never seen before. We want the robot to do useful things for us. And such that when it does something useful and something good, we'll tell it good job. And when it does something bad, like breaking a plate or a glass, we tell it that it did a bad job. But maybe to make things a little bit even more concrete than that, maybe we just want the robot to make us a bowl of cereal. This is like really simple, and maybe doesn't really seem ambitious at all. But at the same time, this is like really a trivial job for a human, but demands intelligence, demands common sense for artificial agents, for robots. So how can we think about getting a robot to do this? I think that this is kind of, in many ways, a very long-term goal and a very challenging goal. But I do think that there are steps that we can take to try to answer some of the open questions regarding this problem. So for example, if we just are having good job and bad job as a reward signal, that's kind of the really easiest thing to do. How can we think about recognizing the multitask structure underlying our experience? So in many ways, there's just a single reward function of whether or not the robot is doing a good job or a bad job. But underlying the robot's experience and the things we want to do, there exists many different tasks and many different objects and many different things the robot should use. And it should recognize that structure without task boundaries in a way that allows it to more efficiently solve the task. So this is kind of moving back towards the original reinforcement learning problem statement. One initial way that we can start to think about this sort of problem is to adapt to windows of experience, so just treat a window of experience as a task, and use that to recognize when you're kind of in one task versus another task. So for example, if you have, you could kind of take data on different terrains. You know that there's some sort of temporal continuity. So if at one time step you're on one terrain, it's likely that the next time step you're still on that terrain. And then you can use meta-learning across those windows of time such that you can quickly adapt to the most recent experience that you've seen. And so this allows you to kind of recognize the structure by just making this temporal assumption. And so you can adapt to a new situation, such as when you are missing a leg. And I think that maybe this was covered in one of your previous lectures. So this allows you to adapt without task boundaries. But this is kind of a very initial step and a somewhat naive approach to do this. And I think that we can probably do better. It's a little robot called a Velociroach. OK, so this is kind of one thing that we need to do is recognize the structure underlying monolithic experience that allows us to much more efficiently solve standard reinforcement learning problems. Now, if we want to make a bowl of cereal, and this was actually mentioned earlier, we have a longer horizon problem. We don't just have one primitive, one skill. We need to actually perform different skills in sequence. And we need to reason on longer time horizons. So one way that we can think about doing this is maybe we already have acquired those previously short skills, and we just need to sequence them together. We need to bootstrap from that experience to perform longer and longer horizon tasks. So what we can do is, this idea and this kind of problem statement has been very widely studied, but one approach that you can imagine doing is optimizing over sub-goals that make a longer horizon task easier. So for example, if this is your state, this is your goal state, you could imagine trying to generate intermediate states that might make this problem easier, such as something that first knocks the objects off of the table and then closes the door. And then if you have these sub-goals, you can then kind of perform the individual primitives, such as first knocking over the objects, and then starting to close the door, and then finishing closing the door. That makes a longer horizon task much easier by stringing together the things that you already know. And then lastly, if we want our systems to be able to continuously, to be able to perform very complex tasks, they need to start somewhere. They need to kind of start basically where we are now at least, and continuously improve and continuously learn. It isn't going to be that we can that we can learn from scratch for each thing that we do. We need them to continuously build upon what they've learned previously, and ideally also become faster at learning as they continue to learn, right? If we're going to be continuously doing some sort of lifelong learning, it may be that if we're continuously running the learning process and we're not getting any faster at learning, then it may take us a very long time to get to this kitchen. So one way that we can think about this is meta learning allows us to quickly adapt to new skills. Lifelong learning allows us to kind of think about the problem of performing a sequence of skills where you're trying to measure, like, can I get good zero-shot performance at a sequence of skills? But can we think about combining these such that as we're learning a sequence of skills, we're also simultaneously getting faster at learning? And we have some initial work that starts to formulate that problem setting formally, such that you're actually evaluated on your ability to quickly learn new tasks, such that at the beginning of lifelong learning, you're slow because you're learning from scratch, but at the end, you're getting faster and faster at learning, such that you're accelerating this lifelong learning process. OK. So that's it. Those are, I think, some of the steps we can take towards the big open challenges in reinforcement learning and robotics. I'd like to thank my students and some of my collaborators, and happy to take a couple more questions. Thank you.
All right, any questions for Chelsea?
Question if we have time, otherwise I can hold it. All right. So in Meta World, in addition to this idea of creating a denser distribution of tasks, the tasks themselves, I guess like their optimal policies would be in some type, they're on some type of manifold in parameter space. Is there have people looked into maybe smoothing that task manifold so that it would help for generalization? And to make it concrete for mammal, if you have something very complicated, then your gradient steps might be tough to like get to the optimal policy after one-shot learning. But if you had something smoother, it might be simpler.
So you're suggesting to smooth the task distribution or smooth the prior?
smooth the task, it would be like smoothing a representation of the task distribution. Because the task distribution itself is whatever it is. But your model, you're trying to learn some type of representation.
Yeah.
Could you smooth that?
Yeah. So I don't think that there's a lot of work in this direction, but I think it's quite interesting. One thing that you could imagine doing is, if you have your meta world task distribution, can you invent new tasks that fill some of the gaps, like a semi-supervised meta-learning setting where you're both constructing tasks similar to the unsupervised meta-learning stuff that Sergey talked about, I think, in a previous lecture, as well as using the tasks that you have in the benchmark. On the algorithm side, I think a little bit closer to what you're imagining, you could also imagine broadening your prior or smoothing your prior such that instead of maybe having like spikes around certain tasks, you try to fill in the gaps. And I think that some of the work that I talked about on preventing memorization may have a similar effect. Basically trying to regularize the prior that you're learning to be simpler in a way, essentially. And happy to talk more about that offline.
Sure, thanks.
Do any of like current meta-learning algorithms sort of utilize curriculum-like frameworks? So like proposing increasingly difficult tasks, so like maybe it's easy to learn something simple at first and then you can sort of build up more complex understanding. Yeah,
so there's only one work that I'm familiar with that does that, and it should be coming out on arXiv like imminently. It's basically it's kind of similar to the unsupervised meta-learning stuff that you saw in a previous lecture, but also trying to couple that with the meta-learning process such that you take into account how capable the meta-learner is when you're proposing unsupervised tasks, such that they can propose more and more complex unsupervised tasks and increase the complexity of the meta-learner. I'm not familiar with other works that study this problem in the context of meta-learning, but there's also a wide range of works that study curriculum learning and curriculum generation, and that work I think is also can provide a lot of inspiration. Yeah.
So one of the ways of adding some sort of generalization and exploration of the parameter space is using a hyperprior. So do you explore some of that, like using a hyperprior on your prior? So that would require some additional trials, but it would also open the space for the probability distributions to be a lot bigger.
Yeah. So the work that I talked about on memorization, in effect, what it is doing is it's actually putting a prior on the weights of the meta-learner, which you could view as a hyperprior, and it's trying to regularize that kind of weight distribution to be simpler in a way. And so you can kind of view that sort of regularization as encouraging it to have to fill the space of meta-learners and allow you to generalize better to tasks. The motivation was a little bit different, but it seems conceivable that could also help in settings where you want a smoother space. You could also conceivably try to learn a hyperprior, and that would be like a meta learning kind of thing. But then you may have more problems than you created, or more problems than you're solving, because you now need not just one distribution of tasks, but a distribution over a distribution of tasks, conceivably. Yeah.
I have a question about compositionality. So in the cover case, you almost know what exactly the language would look like, and that relies on the fact that you have a primitive of the language. So, as previous experience has shown, so for example, neuromodular network works very well on this limited domain, but does not generalize very well on open domains. So, do you think, like in the future, we should have more time to build more primitives, or we should collect more data about natural language to truly build an agent that can do instruction following?
Yeah, so that's a good question. I think that there are really a number of challenges ahead for instruction following, and that kind of some of the work that I showed was really just a first step towards thinking about it. I think that we should go more of the latter of what you're suggesting. So I don't think we should necessarily construct what these primitives should be and train on those. I think that we should more think about how an agent experience can be augmented with language information, and using that language information, ideally in natural language, such that users can provide it, using that language information in a seamless way to accelerate and improve the generalization of the reinforcement learning process.
Okay, let's thank Chelsea one more time. Is the HCAN representative in the room? Yes, please. So, okay, so that's it for the lecture. We're going to have some number of minutes for you guys to fill out your course evals. So those of you that are actually in the course, please do hang around and make sure to fill out your course evaluations.